Welcome to Notes 11.6. Today we are going to talk about the areas of regular polygons, which is something you should be somewhat familiar with because we've covered it before when we talked about special right triangles. So let's talk about first what happens when we inscribe a regular polygon inside a circle. There are some angles formed. First off, we have this angle right here, angle EGF. It is a central angle, so it is equal to the measure of the intercepted arc. Well, if this is a hexagon, it intercepts my circle 6 times. There are 6 vertices, which means that I can find this central angle by taking 360 and dividing it by 6, and that gets me 60 degrees. EGH is half of that. All right, this altitude right here bisects this central angle, which means that EGH is 30 degrees. And then HEG obviously is going to be complementary to that because we have a right triangle going on. So HEG is going to be 60 degrees. All right, let's talk about what happens when we have a regular polygon. Well, first of all, you'll remember that the formula for the area of a regular polygon, if I can get my pen to work, there we go, is 1/2 AP. And the parts we need for that are we need the apothem and we need the perimeter. And so frequently in order to find the perimeter, which means we've got all the sides, we also need the radius. All right, so if we have any of these parts, then we can go ahead and we can find all the rest of the things that we need to use the formula. And you'll remember that this perpendicular bisector right here, that's my apothem. The distance from, so the apothem is the perpendicular bisector of side. And then the radius goes from the center to a vertex. Okay, so it is the hypotenuse of the right triangle that is formed. Now this formula that we've been talking about, we talked about it before in reference to 3 specific polygons that formed, had special right triangles inside of them, that when we found this right triangle is a special right triangle. And those 3 with the special right were a triangle, a square, and a hexagon. This formula works for any regular polygon, not just those. It's just that those 3 have a special right triangle formed by the apothem and the side, the half side, and the radius. All right, so for example, if we have a coaster that's an octagon, well, we can still use that formula, area equals 1/2 AP, is just not going to contain a special right triangle. Okay, so we're given a wooden coaster. It's an octagon. It's got 3 centimeter sides and a radius of about 3.92 centimeters. And we need to know the area of the coaster. All right, well, what we don't know is we don't know our apothem, but we can go ahead and we can find it. If we drop an altitude that bisects the side, then we're looking for the apothem. We know that the half side is going to be 1.5 centimeters, and we can go ahead and we can find our apothem by using the Pythagorean theorem because we have a right triangle, we know 2 of the sides. So I've got 1.5 squared plus a squared equals 3.92 squared, which means that a squared equals 3.92 squared minus 1.5 squared, and then we just take the square root of that. So we're going to go ahead and put that into our calculator. Move my calculator out of the way here. All right, so I want to take the square root of 3.92 squared minus 1.5 squared, and that gives me an apothem of about 3.6. All right, so hang on, let me see more exactly than that. All right, so it's 3.621 blah 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 and change. Okay, ideally I want to round as late as is humanly possible. So I've got this in my calculator already. We know we're going to multiply it by the perimeter. So we need to know what our perimeter is really fast. There are 8 sides. Each side is 3 centimeters. So my perimeter is 3 times 8, which is 24 centimeters. So I'm going to plug the perimeter and the apothem into my formula right here and go ahead and type it into my calculator. So I'm going to take 1/2 times my answer that I just got previously, so that puts the entire thing with the decimal and everything, and then multiply that times 24, which was my perimeter, and hit enter. And that gets me my answer because I haven't rounded, so it gets me the most precise answer that I'm going to get under these circumstances. So my area is about 43.46 centimeters squared. So approximately 43.46 centimeters squared is the area of my coaster. So in the previous problem, they gave us 2 of the sides of the triangle, but in this one, they only give us 1 of the sides. We've got a regular nonagon, and it's inscribed in a circle with a radius of 5 units. We need to find the perimeter and the area. All right, so how do we do this? Well, we know that this angle right here, this central angle, is going to be 360 divided by 9, which gets me 40. So that central angle is going to be 40 degrees. But what I really want to know is what half of that is. So I'm going to divide that by 2, and that gets me 20 degrees. So the measure of angle, let's say, for example, KLM, equals 20 degrees. Here's why that's important. Because once I have an angle and a side, then I can go ahead and I can use trig to find any other pieces that I'm missing. Okay, so let's find the half side first. From the perspective of this 20-degree angle right here, this half side is the opposite, and the 5 is the hypotenuse, which means I'm talking sine. So the sine of 20 degrees is going to equal my half side, divided by my hypotenuse. So my half side is going to equal 5 times the sine of 20, which means my whole side is going to equal 10 times the sine of 20. And furthermore, my perimeter is going to be, there's 9 sides, so 9 times each of these. Multiply both sides by 9. Can't really see the 1 anymore when I do that. All right, so basically my perimeter is 90 times the sine of 20. All right, so it does ask for the perimeter, so we're going to go ahead and type that into our calculator. So we're going to take 90 and multiply it times the sine of 20. And we get a perimeter of 30.8 approximately. All right, so my perimeter is approximately 30.8 units. Okay, so now I need to find the area, which means I need the apothem right here, right? Because my area, I'm going to use my 1/2 little a big P formula. All right, so from the perspective of this angle, the apothem is the adjacent, and I've got the hypotenuse, so we're going to use cosine. So the cosine of 20 equals my apothem over my hypotenuse. So my apothem is going to equal 5 times the cosine of 20. All right, because we want the most exact answer that we can possibly get, we want to round as late as possible, we're going to leave both apothem and perimeter in this format. So when we plug it into our calculator, we're going to plug in 1/2 times 5 cosine 20 times 90 sine 20 to get the most exact answer that we can possibly get for our area. So let's go ahead and do that. All right, so it is 0.5 times, what do we say, 5 cosine 20, close parentheses, times 90 sine 20, close parentheses. and we get 72.3. So my area is approximately 72.3 units squared, and that's my final answer for that one, and this was my final answer for my perimeter. Please make sure you understand why I plugged this in rather than rounding. All right, using the same method that we just used in the previous problem, I would like you to go ahead and solve this problem. So go ahead and do that and come back when you have an answer. Hit pause now. All right, so you should have found that this angle right here was 36 degrees. Our half side is 4. We're looking for the apothem, which means that we find it using tangent. So tangent 36 equals the opposite over adjacent, 4 over apothem, which means my apothem is 4 divided by the tangent of 36. My perimeter, there's 5 sides. They measure 8 each, is 40. So I go ahead and plug those in for A and P, and I get an area of 110.1 meters squared. So now we're back to our regular polygons that do contain a special right triangle inside them, which means that they can be solved using a radical. And remember, if you can solve with a radical, then you must solve with a radical. So although you could use trig to do these, we're not going to. Okay, we've got an equilateral triangle with a radius of 16. So I've drawn my right triangle. Remember that the radius bisects this angle. If this is an equilateral triangle, this is a 60-degree angle, which means that this part is 30 and this part is 60. This is all review, so I'm going to go fairly quickly. All right, so if my radius, which is my hypotenuse, is 16, then my short leg must be 8, which means my apothem is 8 meters. And my half side is going to be 8 radical 3 meters, which means my whole side is going to be 16 radical 3 meters. So my perimeter is going to be 3 times that. I get 48 radical 3 meters. And my area is going to be 1/2 my apothem times my perimeter, which means that my area is 192 radical 3 meters squared. All right. Next, we have a square with a radius of 6 radical 2. So I'm going to draw the triangle. And my radius is 6 radical 2. And I want you to find all of these pieces for the notes check. Keeping in mind that this triangle is a 45, 45, 90 right triangle. I want you to do the same thing for the regular hexagon. Let me draw the triangle. So there's my apothem, there's my radius. This time I'm given a perimeter of 48, so the side length is pretty easy to find. This is a special right triangle. You need to figure out which one it is, and then you need to go ahead and give me all of these answers in the notes check. That concludes our notes for today. Please be sure to go on and do the notes check. And if you have any questions, ask in class. Thanks.